Hi friends, welcome back to Edupedia World. The previous lecture we saw the fundamental concepts about refraction and some cases of refraction. Today we will discuss it in a more organized fashion, as in we'll learn about the laws of refraction. We'll understand those laws. We'll see the Snells Law. We'll also see the relation between the refractive index and speed of light in different media. And finally, we'll conclude today's lecture with understanding about the principle of reversibility of the path of light. So let us start with today's lecture. We have a set of laws called the laws of refraction, which govern the phenomena of refraction. Let us see what the laws state. The first law of refraction states that the incident ray the refracted ray and the normal at the point of incidence all lie in the same plane. Normal at point of incidence all lie in same plane. And the second law states that the ratio of sine of angle of incidence angle of incidence to the sine of angle of refraction is constant for a pair of medium, and this constant for that pair of medium is called the refractive index of that pair. And this constant is called the refractive index for the second medium. For the second medium with respect to the first medium. Okay, so this can be mathematically stated as sine of angle of incidence upon the sine of angle of refraction is equal to refractive index, which is denoted by a Greek letter mu, and since we have two mediums 1 and 2, and this is refractive index of second with respect to first, we denote it like this: refractive index of second with respect to first. So this means that the ray of light is going from 1 to 2. Alternatively, refractive index is sometimes denoted by n, and the notation is similar: n to 2, 1 to 2. So refractive index of second with respect to first. This mathematical representation is known as Snell's Law. Snell's Law. Now let us understand what the laws of refraction actually state. The first says that the incident ray, the refracted ray, and the normal all lie in the same plane. Quite obvious if you have seen the previous lecture. This is the incident ray. If this is rarer and this is denser, then this is the refracted ray. This is incident, this is refracted, and this is the normal. All the three lie in this plane of the screen. So that is what the first law states. The second law states that sine of angle of incidence to the sine of angle of refraction is a constant called the refractive index. So basically this angle, sine of angle of incidence to sine of angle of refraction for medium 1 and 2 can be defined as mu 1 2. Okay, and since this is a constant, the mu for the pair is a constant, depending on what the sine of angle of incidence is, we can find exactly what the sine of angle of refraction will be. Hence we can exactly pinpoint what the angle of refraction will be. Okay, so let's imagine that as in this case the refractive index of second medium is larger than the first medium, right? The refractive index is basically, this is optically denser, so refractive index is higher for second with respect to first. Therefore this is greater than 1. Therefore sine of I should be greater than 1. Rather, sine of I should be greater than sine of R, which means I is greater than R. Therefore when light is going from a rarer to a denser medium, it bends towards the normal. If this were denser and this were rare, then this would have been less than 1 and it would have moved away. So this is the laws of reflection, the two laws. We have seen what the refractive index is. It is the refractive index of second medium with respect to the first medium is defined as the sine of angle of incidence upon the sine of angle of the refraction. Okay, now let us see what is the relation between speed of light in different medium and refractive index, right? So first let us compare the standard refractive index, that is the refractive index with respect to vacuum. If the refractive index of a medium is stated with respect to vacuum, we do not need to mention these mediums. We just mention mu. This means refractive index of a particular medium which we are discussing about with respect to vacuum. We don't need to write vacuum and the second medium. It's automatically understood. And mu in terms of velocity can be said as velocity or speed of light in vacuum upon the speed velocity of light in that medium. Okay, so the mu will always be greater than 1, or at least it will be equal to 1. Why? Because the speed of light can never exceed that of the speed of light in vacuum. So this will always be either greater than or equal to the denominator. Therefore mu will always be greater than equal to 1, right? When will it be equal to 1? When we are discussing the refractive index of vacuum itself. In any other case, the speed of light will be less than the speed of light in vacuum, hence the refractive index will be greater than 1 in those cases. Okay, so now that we have seen what refractive index of medium is, how it is defined, let us do a quick numerical to understand it better. Let's say that the refractive index of glass is 1.33. Okay, we know that the refractive index of glass is 1.33. The question asks us to find the speed of light in glass. Pretty straightforward, right? We know the refractive index of glass. We can write it as mu g or mu glass, and that is 1.33. We know that the velocity of light in vacuum is denoted by c is equal to 3 into 10 to the power 8 meter per second. Okay, this I should have mentioned here. It is always 3 into 10 to the power 8 meter per second. This is a universal constant. Actually, it is a little different, 2.99 something, but for all practical purposes of our lecture, 3 into 10 to the power 8 will suffice. What do we need to find? We need to find the velocity in glass. This is asked. So we can directly apply this relation. We can write 1.33 is equal to 3 into 10 to the power 8 upon v, vg or v, velocity of glass. If we manipulate this, v can be taken there, 1.33 can be taken here. This will give us 3 into 10 to the power 8 upon 1.33, which effectively 1.33 can be written as 4 upon 3, right? So we can take it as 9 upon 4 10 power 8, which is 2.25 into 10 to the power 8 meter per second. So if the refractive index of glass were 1.33, then the velocity of light in that glass would have been 2.25 into 10 to the power 8 meter per second. Okay, now that I realize, I actually mentioned the refractive index of water here. 1.33 is the refractive index of water. The refractive index of glass is somewhere around 1.5. So pardon that mistake, but the theory holds true even then. It's just that if I were to find for the glass, then I need to change 1.33 to 1.5. But for completion's sake, let's take it as the refractive index for water is 1.33. Then the velocity of light in water will turn out to be 2.25 into 10 to the power 8 meter per second. So we see how the velocity of light is related to refractive index, right? Now we have seen here the refractive index with respect to vacuum, but in the Snell's law the refractive index can be any medium with respect to any other medium. So ideally we would like to understand the relation between the velocity of light in two different medium and the refractive index of those two mediums, the relation between them. So that's what we will do next. So now let us see the relation between refractive index of two mediums, pair of two mediums, and the relation between velocity. The refractive index of medium 2 with respect to medium 1. This is how it is represented. Refractive index of second medium with respect to first medium is the speed of light in medium 1 upon the speed of light in medium 2. Okay, so refractive index of second with respect to first, speed of light in medium 2 upon the speed of light in medium 1, V1 upon V2. Now this, what can we do? We can do some manipulation here. How? We can write this as C upon V2 the whole divided by C upon V1, right? And C upon V2, as we just discussed now, is the speed of light by the speed of light in medium 2, speed of light in vacuum by speed of light in medium 2, and that is refractive index of second medium, and this is refractive index of first medium. So what we have got here is that the refractive index of second medium with respect to first medium is refractive index of second medium with respect to vacuum upon the refractive index of first medium with respect to vacuum. So this is an important take home that I'll write it here. Refractive index of second medium with respect to first medium is the ratio of the refractive index of second medium with respect to vacuum to a refractive index of first medium with respect to vacuum. Okay, so we can find the refractive index of a combination of different mediums if we know the refractive index of those two mediums with respect to vacuum. Now to understand this better, let us do another question here. So we know that the speed of light in water is 2.25 into 10 to the power 8 meter per second, and speed of light in glass is 2 into 10 to the power 8 meter per second. Find the refractive index of, let's say, glass with respect to water. Okay, so refractive index of glass with respect to water. How can we do this? We can apply this straightforward. The refractive index of glass with respect to water. So this is my first medium, this is my second medium. What this means is that the light is going from water to glass. So it is going from a rarer to a denser medium, low speed, high speed to low speed, Therefore, this should be greater than 1, right? Let me see how this turns out. Is speed of light in medium 1, so speed of light in water, which is 2.25 into 10 to the power 8 upon 2 into 10 to the power 8, which is, as we can see, is greater than 1. This is basically 9 upon 4 into 2, which is 9 upon 8, or alternatively we can write it as 1.125. So the refractive index of a second medium with respect to the first medium can be found out like this, like the speed of light in first medium upon the speed of light in second medium. Alternatively, if the question said that the refractive index of what is the second medium, the glass, is 1.5, if it was given that mu g is 1.5 and mu water is 1.33, then again I would have written mu of g with respect to w is mu of g upon mu of w, and that would have given me 1.5 upon 1.33, and effectively 3 by 2, 4 by 3, effectively I would have got the same answer. So either if you are provided with the speeds in the two medium, or you are provided with the refractive index of the two mediums with respect to vacuum, we can find the refractive index of one with respect to other. Now, an important concept which we can derive from here itself is that the refractive index of, let me write it in a different color, the refractive index of medium 2 with respect to medium 1 is 1 upon the refractive index of medium 1 with respect to medium 2. Okay, why is that? Why does this have to be so? This has to be so because mu of 2 with respect to 1 means what? Mu of 2 with respect to 1 is the speed in medium 1, speed in 1 upon speed in 2, and mu of 1 with respect to 2 is speed in 2 with respect to speed in 1. Therefore, we can clearly see that this has to hold true, that is, refractive index of second with respect to 1 has to be reciprocal of refractive index of 1 with respect to 2 for this to be correct. Okay, and this concept that the refractive index of one medium to the other is reciprocal of medium refractive index of the other to the first is called the principle of reversibility of light. That is the cause of the principle of reversibility of light. And what the principle of reversibility of light states is that the path of a ray of light is reversible, as in let me do it here. Suppose this has to be a straight line. So suppose a light is going like this. So this has to be rarer and this has to be denser. So if the light is going from rarer to denser medium in this path, and somehow if we exactly reflect it back, then at this point it will refract back exactly by this path. Okay, this is the principle of reversibility of light, that the path of light will be retraced throughout. If it were to follow the same path in one segment, right? And how can we say that this is actually true? We can say that this is actually true by using this relation. How come? Let us see. In the first case, when this is going from here to here, if this is I and this is R, then what we can say is that, and this is 1, this is 2, so mu 2 1 is equal to sine I upon sine R, right? And when we are going from 2 to 1, then this is angle of incidence and this is angle of refraction, but I am keeping it as R and I itself. What will happen then is that mu of 1 with respect to 2, because from 2 to 1 it is going, is equal to sine of angle of incidence is now R, sine of R upon sine of I, right? And what we can see, or let us do it like this, let us make this as I dash and make this as R dash. So this will be I dash upon R dash, right? And this are reciprocal of each other, so sine of I upon sine of R is equal to reciprocal of this, so which will be sine of R dashed upon sine of I dashed. Okay, and since this and this are equal, and we already said that this part is being retracted, it is following the same path, so R and I dash are same. It is given that R is equal to I dash, so when R is equal to I dash, then I has to be equal to R dash too, right? This implies this because of this, right? So what we see here clearly is the reversibility of the path, and that is because of this, because the refractive index of second with respect to first is reciprocal of the refractive index of first with respect to second. Okay, I think we have done a lot for today's lecture. In the next lecture, we'll take it further from here. Goodbye for now.